All right, then we move on to P2P. So we will talk about why P2P is better than the old method. Then we talk a little bit about BitTorrent and distributed hash tables and go down from there. So P2P. But P2P, if you have not done it, you are not living in this world right now. So if you are alive and well, and if you need any information, you got to get it by P2P. And P2P is actually better than the old method, as I will show you in a minute. Basically, what happens is when you want a file, for whatever reason, currently it works, the way BitTorrent works is that you go to a website and they tell you that here is the torrent. Torrent is nothing but a file which has all the information about that file. So it is not the file that you want. You want a movie which is 722 megabyte long, and that file is only 40 bytes or 100 bytes long. Torrent. Once you get the torrent has much information about that file, and one key piece of information is where the tracker is. So one piece of information in that torrent file, if you can read it, says that all information about this particular copy of the movie is at this particular website. Not a website, torrents, whatever, torrent server. Right? So you go to the tracker, and the tracker has a list of all the people who are exchanging the file right this second. All right. So you get the list of all the people who are tracking this file, who are exchanging the file right this second. Then you contact them and connect them and say, "Can I also have a piece of this file?" Right. So torrent. So now this is a name actually. So although that file which has an extension torrent, we call it torrent file, but torrent is the whole set of peers that are exchanging that file. Right? Some of them are called seeds and some of them are called leechers. Who are the seeds? Everybody should know. The ones that have complete files. Right? And leechers are the ones that have incomplete files. And so there is some kind of, just you give me one, I will give you one kind of deal, which I will talk about in a minute. So that's how you exchange the information, and finally the leechers will become the seeds, and there will be more seeds or less seeds depending upon when the seeds leave, and all this is being monitored by the tracker. Tracker keeps track of all the people who are coming in and going out of that place, of that group. Now for every file there is a separate set of torrents, separate set of seeds, for separate sets of tracker and everything else. Okay, so you have to do that. Now, so let's see how it saves the network bandwidth. So P2P saves the network bandwidth. So if you have one server which has the original file, and you have n people who want it. In the old method, everybody has to go to the server and get the file. So here's the thing. So if you go to the server, how many bits you will have to send? How long will it take? Each of these users has a downlink speed of dn, and actually this is just the opposite. It has a downlink speed of un, uplink speed of dn. Does that make sense? Uplink speed is ui and downlink speed is di. I think I would change the arrow directions here so that uplink becomes like that, downlink becomes like that. This is correct. D1 is correct. D1, U1, D2, U2 is correct, and US is correct, but this one is wrong. N is wrong. So anyway, so these are the speeds. Everybody has a different speed. But anyway, if you take the D min, of all the downlinks, that will take the longest to get the file, and it will, if the file size is f, speed is d min, this is how long it will take to get that file. And since n times f bit have to be transmitted, what is n? N is the number of users and f is the file size, so n times f bits have to be sent by the server, and the server's speed is only us. So you divide by that, so maximum of that much time will be taken if you want to do client server. That is how long it will take for the file to go to all the people. On the other hand, if you do P2P, then only one client has to get it. So only one file has to be sent, and that can be sent at the speed of f upon us. And if that happens to be the bottleneck, then that will take f upon d min to receive. And then, although NF bits are being exchanged, but everything is being done in parallel, and therefore all these uplink speeds will add up, and that is how long it will take to upload the files. Right. So the minimum of those three numbers in the bottom will give you how long it will take to get the file by P2P, and the second number will show you how long by client server, and you can plot these two numbers for any particular case. And so P2P is here in the bottom, blue curve, and client server is here. So unless you had one client, P2P always wins. So basically the idea is distributing the load. So the idea is client server, the old method is, at least in terms of delay, is not very good. Right? And although in terms of traffic, let's see what happens in terms of traffic. Let's just see the previous slide. How many bits are transmitted in client server? The file size is f, n times f. And how many bits are transmitted in the P2P? Same nf. So the total traffic number of bits is same, but this one is all coming from one location. So there is a lot of congestion, whereas this is distributed traffic. P2P is distributed traffic, but client server is all coming from the server, and therefore that causes a bottleneck. So in terms of bottleneck capacity, again P2P wins. So alright, so I think we already talked about how BitTorrent works. The way BitTorrent works is that the peers are the node that participate in a file distribution. Torrent is the set of all peers. Torrent file is the file which contains the name of the tracker and all the file details and everything else. Files are segmented into equal chunks. So that's the new word, chunk. So the files could be different sizes, but whenever we want to get something, we get in 256 kilobyte unit. Everything is sent in 256 kilobyte unit, and that is called a chunk. Alright, we already know seeds, leechers and trackers. So basically the steps are that if you want to get something, you first find the torrent for it. You go to Google or you go to some other place and you find the torrent for whatever information you're looking for, and then that torrent has the name of the tracker. So once you upload into your BitTorrent client, it goes to the tracker and gets a list of peers. Now tracker may have 2,000 peers, but it will not give you the whole list. It will give you some top 50 maybe. Then you set up the TCP connection with those peers in parallel, and each peer will tell you what chunks they have. So somebody has chunk 1, 3 and 5, some people have 5, 7 and 8, so you get the whole map. And then you request the least available chunk first. So that's the rule, is that if you, because it's quite possible that the guy who had just chunk number 1 can leave any second. So get that chunk number 1 first, and before he or she leaves. So get the rarest first. Every 10 seconds you recalculate the receiving rates. Every 10 seconds you calculate the receiving rates. So you calculate what rate I am getting from this user, from that user, from that user, and from that user. And unchoke the top 4 senders. The top 4 people who are sending to me, I will send it to them too. Alright, even though it is the same file, you don't have it, I don't have it, but I am collecting pieces of it, you are collecting pieces of it, and I will help you get faster because you are helping me get faster. Alright, so I will unchoke the top 4 senders. Every 30 seconds, I will randomly select a peer and unchoke it. So while the top 4 are by mutual this one, but I will take one random one and add it to the group because I want to see whether they will respond in kind. If they respond in kind, then they get in the top 4. So this way it helps find the high rate neighbors. So this way we find out who are the neighbors who have high speed links and who can give us faster. So basically if there are, let's say I got this list of all 63 senders or peers, I will try connections with them and I will see how much is coming in, but those guys are too far away. I'm not getting, but I'm getting too much from these 4 people. I will concentrate on these 4. Yeah, randomly select one more. Yes, every 30 seconds you do randomly one more. And you could have more than 5 too. Basically what will happen is you take the top 4 then. So basically the people who are, so I mean I could be, so if you go to BitTorrent, it tells you how many it is connected to. Seeds, and so there is a number. It says, okay, I have a total 50 and I'm connected to 10. Those numbers are visible. I mean, you can see it in your client. And so it is connected to a lot more clients, but then it takes the top 4 and then basically it unchokes them in the sense that it sends them more information basically than the other people, right? So the more upload. So here the interesting thing is that if your upload speed is very low, then your download speed automatically becomes low. Alright, if you increase upload, then your download increases, but I have found that basically what happens is your computer becomes so busy uploading that it doesn't have capacity to download. So you get bottlenecked that way. So you cannot have upload too much either. Alright, so there is some optimum for the upload and download relationship. P2P uses a technology called distributed hash table. And so I wanted to discuss that briefly. Everybody probably knows the hash table is that if you have a key that you want to look up in a table, you could keep a very big table and every key will have its own place. If the key is 10-bit long, you could keep a table which is 2 raised to 10-bit long. If the key is 32-bit long, you could keep a table which is 2 raised to 32-bit long. If the key is 128-bit long, you could keep a table which is 2 raised to 128-bit long. But that would be a very, 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 very long table. So if the key is big and the table is small, the way we do that is by using a hash function. What hash does is, hash is a function that maps a big key to a small key. A big number of bits to a small number of bits in a very unique way, so that 2 big keys will not really clash and hash to the same value. They could, obviously, because if you are going to take 128-bit and hash them to 10 bits, 2 128-bit quantities could hash to 10 bits, but the probability is small. We just somehow, a good hash function will reduce that probability. A bad hash function could take all 128-bit quantities and put them into the first cell right there. Just hash everything to 1. Right? That would be a really bad hash function. And a good hash function will try to be such that all these cells, if you have a table which is 10-bit long, all the cells will be used up. And if you have 2 raised to 10 keys. If you have more keys, then obviously none of the hash function will be able to avoid the clash, right? So your table has to be of the size similar to the number of keys that you're really going to use. And so if you are going to use only 5 keys, the table doesn't have to be 50 of size 50. It could be maybe 8, 16, something like that. And so what do? So we use hash function to reduce the key size, and we look up that hash in the table. So let's say hash says number 10. So you go to the 10th entry, and then you look up the key there where the exact value is stored, and you match. If it matches, you got the right entry. And for that entry, you might have other things, such as if by the name of a person, it will have a social security number, their bank account number, and so on and so forth. So that is what you use the keys to look up, right? You are using the whatever you are using, maybe social security number or name. You hash it to a number, and in that entry of the table, you expect to find everything, right? It is quite possible that the key doesn't match, because another key had already occupied that position. So then there are ways of finding the next location where that you should be. Generally, simplest thing is to just look at the next location. If the key matches, it doesn't, then go to the next location until you find a match. Generally, hash is show good, and your key table is sparsely populated, and this table is sparsely populated such that you should be able to find the match on the very first location, right? You take a big key, hash it to a small number of bits, that gives you the index of the end table entry, and if not that one, maybe the next one, maybe the next one, maybe the next one, right? So you reduce the searching time. The biggest thing is there is no search, because otherwise you can do a binary search. You could arrange the table in an ordered key manner. You could sort it out. Sorting is a long operation for these things. And then you go through binary search, which take log 2n, where n is the number of entries. Operation, but hash just gives you right away in one operation. And let's say hashes are used whenever you have large size keys to be looked up into a small size, into a table. All right. So let's see. We covered everything. Hash tables are used to find an entry in the table. Distributed hash tables. Now, what if the table is so big, like a DNS, domain name server, which is a big table, and not everybody has a complete table? So the table will be distributed, right? So what you need is a distributed hash table, DHT. Distributed hash table means that one computer may not have the whole table, and it may have to go to some other table to look, some other place to look it up. So we'll talk about the distributed part in the next slide. But database is partitioned and stored in many peers, many computers, has the key to the peer, to find the peer that has the key, and then the peers are numbered from 0 to 2n minus 1, and therefore the keys are numbered similarly. And so basically what you are doing is, if you want to find a file, every file has a key, right? So you want to find out who has all the information about this particular file. So you hash that and you find the peer, right? So one way to organize a distributed hash table, DHT, is a circular way. So this node has all the information about the keys that begin with 0001. Well, let's assume simplicity like that, but it is not always that simple. So let's say this is 001, this is 3, 4, 5, 8, 10, 12, 15. Right? Obviously these, this is like this 1, 3, 4, 5, 8, 12, 15. So since number 2 is missing, 2 will be with one of these two with some kind of formula which says that 2 will be either with this or 3, and then 4 and 5 and 6 is not there, so 6 will have to be divided. So somehow the keys have to be divided among the people who are present. Okay, and the people do come and leave. That's another problem, is that 12 is there right now, but probably can leave at some point. People are going to shut down their computer when they want. So basically people have to find out who has the key. So first thing we do is we hash it. We hash it and we find out that the number hashes to 12. Well, 12 is there. Let's say the number hashes to 11. So it is quite possible it hashes to 12. Then we can just go to 12 and say, look, this key, I want to look it up. Can you tell me the information? And that's easy because 12 is alive and well and has all the keys beginning with 12. But 11 we are not sure. And so just like before, we hash it and we go to 10. Suppose it hashes to 11, we go to 10 and say, do you have it? 10 says, no, I don't have it. Maybe somebody else has it. And so at that point, there will be search, linear search. Just like we did the linear search before here, but the first entry we know where to start. Here we know where to start, and then we do a linear search. And we could keep a complete link to all of these nodes, in which case this will be the number 3 knows about 10, 12, 11, 15, all of these nodes, but it will have a lot of things to remember. Or it could just remember 2 numbers. It could remember 1 and 4, and it could ask 4, what do you can you find out who has the key 11, and then 4 could ask somebody else. So if you didn't keep any other links, you just can go in circle. 3 will ask 4, 4 will ask 5, 5 will ask 6, 6 will ask 7, and so on and so forth. Whoever is alive, right? That will be a lot of time taken to resolve the hash. On the other hand, you could keep more than 2 links. 3 could keep the link for 1, 4, and 8 and 12. All right. In that case, it could go straight to 8 and say, do you know where is 11 key stored? So there is a trade-off of memory versus time. More storage you keep, more links you keep, the less time it takes. But in the simplest case, you just keep minimum. You need to keep 2 links, your predecessor and your next one, and everybody are in a circle. And there are many other methods of distributed hash table. This is a topic of research. People have come up with many other methods and optimizations of how to minimize the time and the number of messages and so on. Yeah, inside the node, they probably have another hash, and that's the simpler part. That is more like this. This slide is about distributed hash table. Well, it is used for both. Actually, I think it is a big table, because when you want to store the key, you do the same thing. You want to find out where should it be stored. You don't want to store the key. You find out where it should be stored and tell that node, now store the key. When you want to look up, you look up the key from that node. So it is one big table. This is one big table which is divided by some formula as to where it should be, and the main problem is that even though we say 11 should have it, but 11 is not there, so somebody else has to keep track of it. So that is the next thing, is that peer churn, is that as the peers leave, we have to keep track of who is alive, who is taking responsibility for what. So when a peer leaves, each peer keeps track of their first and second successors. So for 3, the first successor is 4 and the second successor is 5. And they poll each other, basically. So 3 knows when 4 leaves, the answer doesn't come back, and then it knows that, okay, 4 is gone, so then it says 5. Look, 4 is gone, I am now your successor, and then who is the next successor, then you will know that 3, 5, and 8 are now there. Right? So they keep track of who is there. So you keep track of your first and second successor. You do periodic handshake to verify connectivity. So you say hello, and then the hello comes back, so you know that it's still there. When the first successor leaves, you connect to the second and you find a new second, right? And when a new peer joins, it sends a message to peer 1 which gets forwarded until the right predecessor responds. So when somebody comes back, suppose somebody comes back here, then it will send the message to number 1 and it will go to 1, 2, 3, 4, 5, and they say, oh, you are position 14, so you just join here, your next successor is 15, and next to next is 1. So you are placed in the right place in the table. So when a new one comes in, they find their place. When somebody leaves, the other people who are left, they really join together so that the whole thing remains connected. It's quite possible that 2 successors can leave, then they will basically start, initialization problem where now, I don't know who to talk to. Then when 1 says to 3, when, hello, then it says, well, I don't have any successors anymore. Then it might go backwards, or they will restart the whole organization to figure out who is left. And so the whole circle will be rebuilt from the scratch, right? If 1 leaves, that becomes a problem too, because everybody is going to go to 1 when they want to join if 1 is not there. So hopefully 1 is something which is more stable and not like everybody else who is leaving. So yeah, so there are technologies or there are algorithms for rebuilding and algorithms for starting initialization. Now, so people when they leave, the question was, what happens? Do they give the data to you and then they leave? Yes, that would be nice if they did that. So for example, if 4 could tell 3 and 5 that, okay, I have the data, I'm going to leave, but most people don't tell. Yeah, right. So there's no, see, all those things could be built, but generally when people leave, they leave. So you have to be ready for a crash, right? So the system has to be designed so that the data has to be reconstructed, somehow the keys will have to be rebuilt. And so when somebody says, well, where is the file number 5? It is 4 is responsible, but 4 just came up. You say, sorry, I don't know yet. Right? And then somebody finds 5, and then they say, where to store 5? They find 4. And so this is a continuous process where the answers are not perfect. And remember, this is done only for very large databases. These are very, very large databases. And there is a large dynamics, there is a large changes going on, people coming in and out. All right, so that is about P2P. Let me see, I think we already talked about BitTorrent in detail, and we said that P2P is better because it reduces the delay and it distributes the traffic better than client server. And then we talked about you need hash tables to maintain this P2P stuff. So that ends our P2P discussion. And the summary of this part of the chapter is that the P2P applications are more scalable. They are more efficient when the number of peers is large. Scalable means big. Basically, they can be used when there are millions of people. Server client can be used when there are hundreds of people. For millions, it becomes difficult, and for billions, it becomes more difficult. But P2P keeps scaling. Then BitTorrent, which is just one of the latest kinds of P2P, has peers, trackers, seeds, and leeches. Now you should know what is the function of the trackers, right? Everybody remembers the trackers. When you get a torrent file, the torrent file has the name of the tracker, along with whole description of all the files that are in that torrent. But so you can start somehow from there to get the list of all the seeds and leeches and all that. And then BitTorrent is designed so that automatically people who are close to you, they get connected to you. People who are far away from you get disconnected. And that is done by what is called optimistic choking. Optimistic choking means that you keep track of the top 4 and you do more communication with them, and then you do less communication with people who are sending less to you. Then we talk about distributed hash table are used to find information all over the world, And then the Skype uses the super nodes to keep track of active users, and for users behind the NAT, it provides the relays. So that's the only way you can get into the behind the NAT is by previously set up connection.